Aerodynamics. Remember this is a picture of a drone from the front end. It's coming towards us. We have the weight. When it equals the lift, we have level flight. If we increase the lift, it'll rise. If we decrease the lift, it will descend. We have a little controller, and we just control it that way. Okay, but what I want to discuss now is I really want to get to load factors and understanding that. But first, before we get to that, we have to understand what happens in a turn for a drone. And that previous video did a pretty good job of explaining that. But I'm trying to get to the load factor issue. So, okay, we have this drone. Now it's turning. There's the propeller blades. Makes sense, okay. There's the camera. It's coming at us, and it's going to start turning. We still have gravity going towards the center of the Earth on all planets, even on Mars. Still has gravity. We win the gravity, and then we have to have enough lift to be exactly, if it's want to stay level in a turn, to equal the weight. But now we're actually doing something else. We're turning the drone. So there's another component of lift, which would be the horizontal component. This would be the vertical component of lift. There's a horizontal component of lift. Now, these are what we call vectors. I don't know if you've had, I don't want to get into the advanced mathematical parts of it, but these are vectors, okay? So we have, they have direction and magnitude. Let's just say this is 1, it's an arbitrary. I'm just pulling that number out of my hat. I'm just saying a 1. It would have to be equal to whatever 1 was here. Or if we want to be more specific, we could say this is 20 pounds of weight. This would have to be 20 pounds of lift. Okay. But since we're turning, we have another factor that is opposing the turn, right? And that's called centrifugal force. And we'll say that is, let's say you need, let's just make it easy and say we need 20 pounds of turning force, and that's arbitrary. Don't try to go too far with this analogy. It's more of an analogy. We would have 20, if it's a constant turn, 20 pounds of, that's pounds, LBS, 20 pounds of opposing centrifugal force. Okay, so it gets complicated. We got the way these vectors, you can do this with vectors. You can turn them into a average, I suppose would be fair enough to say. It's easier to visualize. And we would call that, in the case of a drone, I'm going to call it motor thrust. I hope I'm still in the picture there. I am, okay. So we need that much increased motor thrust. And I'm just, again, pulling numbers out of my hat. We need 40 pounds of that in order to counteract 40 pounds of that. What do we call this now? This is where we get that whole concept of load factor or G factor. It's going to increase. This is going to be more than just the weight. Weight was 20 pounds, but the aircraft thinks it's supporting the propeller blades and the structure. It thinks it's supporting 40 pounds. This would be, if you look at the chart, which, yeah, here it is. If you go to on the testing supplement, go to page 3, you'll see the chart here, and it says if it's a 60-degree bank turn, we'll just say that's 60 degrees bank. It says the load factor is 2. So if the airplane actually weighs on the surface, when you're holding it, it's 20 pounds, it will think it's 40 pounds because it's 2 times. The load factor is 2 times the weight of the aircraft. So if you happen to have a 20-pound drone, it would the propellers and the structure would have to support 40 pounds. No big deal. 60 degrees, that's not that big a deal. But when you get up to 80 degrees of bank, it's almost 6 times. At 85, it's 11.5 times. So in order to support that, what's got to happen up here? You've got, as the bank gets steeper, you have to increase the motor thrust somehow for a drone. For a fixed wing aircraft, you have to increase the lift. And how do you increase the lift? In a drone, it's automatically, but it's important for you to understand how do you increase lift on an airfoil. Not a very good job. Is to continually increase the deflection of the wind down, and also this increasing the low pressure means getting a greater angle of attack to increase lift. But we know there's a limit to that, right? Eventually, you can't keep doing that. Eventually, you're going to get to a point where this air is so steep across the wing that it just can't stick to the wing anymore, and it starts, and you lose your lift. That's when we get this term stall. The airfoil has stalled; it no longer can provide lift. So there's a limit to the ability. That's the important part. It's not only a structural thing, but also an issue of angle of attack. Propeller blades cannot provide speed enough to keep this from happening. As the airflow over the propeller blades, as the motor gets to its maximum RPM, this starts to happen. There's not enough airflow over the wing, over the airfoil, so it stops flying. I hope that makes sense. If not, we can talk about it some more in the class after this, or of course, as I've said before, I'm around. You just call me on the phone, text me, and I'll call you. Emails work. You have to be careful, though. There's good information on the internet, but some of the information on the internet is a little bit bogus. But that's the concept that you need to be concerned about. And we'll also need to be able to read the chart. I mean, the chart's pretty simple. You just roll up this number to whatever degree bank, and this is obviously for testing. It's not something that you're going to be out in the field, pull the chart out, and say, well, let's see, I'm going to do a 60-degree bank turn. How heavy it's because of the concept of increasing the load factor, increases the stress on the machine, and also brings you closer, the greater load factor, closer to the stall. And stall is something we want to provide or prevent. So basically, you can do it either way, either side. It's the same chart, sort of, in different layouts. The important part of this graph kind of thing is to be able to read these kind of charts, because the FAA is sort of fond of this kind of graph. Manufacturers use it often as well. So you just run yourself over to whatever bank angle the question is asking. Typically they ask, well, about 60%. What's a 60-degree bank angle? What's the load factor? Well, you go up there, find the curve, then you go back over here, and it's 2. Of course, it says the same thing over here, right? But or they could come up with an odd number. A 30-degree bank turn. Well, you go up here, and it's like, wow, it's sort of hard to read on the graph curve, but over here, 30 degrees is 1.154. So you get your calculator out, because you can have a calculator for the exam, and you punch the numbers in there. And, that's not that complicated. So hopefully that'll be helpful. Thank you.